A circle, by definition, okay? The definition of a circle is the set of all points equidistant from the center, okay? So if you look here, every point that's the same distance away from X makes up our circle, right? A point here, a point here, a point here, all the way around, that makes up our circle. That distance from the center to the circle is called a what? A radius. It's your radius, okay? So we name a circle by its center. So I would call this circle X, okay? You do just a circle with a center in it, then you know it's not the letter O, it's circle X. AC, this length right here, is called a what? Segment. It is a segment. More specific to a circle? Diameter. If it cuts all the way across the circle, okay, that is a diameter. XB, this length here, is a radius. Okay, and here's how I always tell people to remember this, because sometimes people get mixed up with diameter and radius. Which word is longer? Diameter. Which line is longer? Diameter. Okay, so the longer line is the longer word in that circle. The radius is the shorter one. The diameter goes all the way across. Okay, then angle AXB, from A to X to B, this angle right here. Okay, you know this because I've used this term a million times over in this school year. What do we call that?
Supplementary.
What kind of angle? Not supplementary. Where is it?
Adjacent.
On the center, right? That is a central angle. So when we talk about a central angle, we're talking about an angle that's vertex is the center of the circle. Okay, that is a central angle. Okay. This next little chunk, my markings here are not quite legit, but it's the only one that I had available. That's supposed to be an arc, not a point. Okay, so it's just kind of this little arc instead of the pointy thing, but you get the idea. Okay, look at these three pictures. They're very similar. It's the same circle. It's the same lettering, but we're going to look at different pieces of it. So the first one, arc TRS. That means you start at T, you go through R, and you end at S. Okay, so if I start at T, go through R, and end at S, that's my arc. Can anyone tell me what we call an arc that looks like that? It's not major, but it's 180 degrees. We call it a semicircle. Right? It's half of the circle. So when the arc is half of the circle, it's a semicircle. Okay, 1/2 semicircle. We would say the measure of arc TRS, in other words, how many degrees it is 180 degrees. Okay. Okay, when you name an arc with only 2 letters, it's the shorter distance between those 2 letters. So if I start at R, I don't want to go this way. That's the longer distance. Okay, don't go the long distance. When it's 2 letters, go the short distance. So that's this arc right here. Okay, arc RS. We call that a minor arc. And that just means it's less than 180 degrees. Okay, less than a semicircle. The next one, arc RTS. So start at R, go through T, and end at S. That's called a major arc. Okay, and the way we typically find a major arc is because it's such a big number, right? A full circle is how many degrees? 360. So to find a major arc, typically what we do, we would say the measure of arc RTS is going to be 360 minus the minor arc. Okay, so if you just subtract this little piece from 360, you'll get that bigger arc. That's usually the easier way to go. Okay, so let's talk some arcs here. can you tell me a minor arc that you see in that example 1? AB. Arc AB would be a minor arc. What's another minor arc? DE would be a minor arc. What's another one? AD would be a minor arc. There's one more. BE or EB. Doesn't matter what order you put the letters in, okay? So those are the minor arcs. They're less than 180 degrees. Major arcs that have B in them. There's a few options. Now here's the deal. When you name a major arc, notice the difference here. 3 letters, 2 letters. When you name a major arc, you must use 3 letters because we have to know that you're going through the major side, right? The minor, we only use 2 because we always assume the shorter distance. So if I'm going to name a major arc that has point B in it, what would that be? Did I hear ABD? Is that what? Yeah, ABD would be one. Right? So I start at A, I go through B all the way around to D. That's more than a semicircle, okay? Has B in it, arc ABD. I heard other ones. BDA would be one. BDA would be one. What did you say, Whitney? DEB would be a semicircle. If we start at D and we end at B, right? That's half the circle. DBA. We already did ABD. So DBA would be the same arc, just in reverse.
Would EB work?
Say it again.
AEB.
AEB, yes. So starting at A, all the way around to B. So AEB. Okay. I think there's one more. Let's see what we got. ABD. And the other one from A. EBD would be the other one. Yep. Okay, so those are all major arcs, more than half the circle. Okay, now the semicircles. And if you notice up here, okay, a semicircle has to be 3 letters. Why do you think it has to be 3? If I told you BD is a semicircle, what's the issue there?
It's a diameter.
Right, but what if I wrote it like this? There's an issue with that. Do you see it? You could go either way, right? We don't know which semicircle you're talking about. So when you name a semicircle, make sure you use 3 letters. If I said BAD, that would be this one, right? Because we're not talking about a distance right now. We're talking about an arc on the circle. So if I'm talking about this arc, then it's BAD. Whereas if I'm talking about this arc, it's BED, right? No, it would be the arc on one side versus the arc on the other side, right? If we're specifying a certain arc, if I just say BD, I don't know if I'm talking about this one or this one. They're both arc BD, right? But they're not the same arc. They're equal arcs. They're not the same arc because it's a whole new line that we're working with. Okay, so then you also have arc ADE. And you have arc ABE. Okay, so those are your semicircles. Questions on that? Ash, will you do me a favor? Will you push the arrow down on my air conditioning thing a couple times? It's getting a little warm in here. Thank you. Okay, moving on. We got to keep moving here. So if you look at this picture, okay, this arc right here is arc AB, okay? The beautiful thing about arcs is they are equal to their central angle. So if this angle is 95, then arc AB is also 95 degrees, okay? So a central angle will always equal its arc. And then there's something called the arc addition postulate. Okay, and that just says if you take two arcs and add them together, it will equal the whole thing. Just like the segment addition postulate, just like the angle addition postulate, you already really know this. If I say arc AB plus arc, not B, arc BC, it will equal, I should have technically put an M in front of those, the measure of arc ABC, right? If I take this arc and I add to it this arc, it will equal the whole thing, okay? So you're gonna do a little bit of that on this next little piece here. Oh, I didn't put your letters in. Okay, so here's what we're gonna find on number 2. Let's say, and what I'm writing in black is given, okay? So you're not gonna be expected to figure this out, but write it in because I don't have it written in. If I tell you this angle is 60 degrees, and angle TPU is 20 degrees, okay? And that's everything we know about that picture. So you will be given that, okay? And that's not for you to find. You'll be given that information. If I ask you to find arc TR, can anyone tell me the measure of that arc? 60. A central angle equals its arc. So this would be 60 degrees. Okay? What if I asked for arc TRS? That's 180. Look for diameters, you guys. Anything that cuts straight across, that's a diameter, and a diameter is always going to create 180 degrees. So this arc right here, T to R to S, is going to be 180 degrees. It's a semicircle. Okay? So what would arc UTR be?
80.
It's 80. This is angle or arc addition postulate. This one's 20. U to T to R is 60 plus 20, or 80 degrees. Okay? Okay, last one here. What's the measure of arc RS? It's 120. If we know the whole thing, the semicircle is 180, then we just take away the 60 and we get 120 degrees for that. Okay. Okay. So far, so good? Okay, so a formula. You know this formula. You've done this formula. What is circumference of, oh, is this for later? She's not in this class right now. She's in my 5th period. Sorry. Or 6th, maybe? Her schedule changed. Circumference, perimeter of a circle. What's the formula? It is pi. Pi times what? D. Pi times diameter is one that you can use, or if you like radii better, that's area. Pi r squared is area. 2 pi r. Okay, so you may use either one of those when you're dealing with circumference of a circle, which is what we're gonna look at right now. So first of all, you need to know this term, concentric circles. Do any of you watch Friends? When Monica says, you're gonna wanna put those in concentric circles. I'm like, oh, geometry. Rachel's making her little her little dessert thing, right? She goes, no, you want to put them in concentric circles. I want to do this. And she shoves a marshmallow up Monica's nose. No? It's a good part. Good scene. Anyway, concentric circles just means they have the same center. Okay, so this point is the center of both of those circles that you see. This is the radius of the smaller circle. This is the radius of the bigger circle. Okay? Now, we talked dilations. Remember dilations? A dilation was basically saying something grew or something shrunk proportionally, okay? Looking at this, we're essentially seeing a dilation with a scale factor. I'm going to call these different letters because you can't say R over R, okay? So we're going to call this one K instead. And we'll call this one H, just so we'll get the R out of there completely. You always do the bigger figure over, not the bigger, the image over the pre-image, okay? So the first figure should go on bottom. And this one, I'm not telling you what your top or bottom would have been, what your starting figure was. But if we're dilating this, we're gonna say our original figure is the smaller circle, and it dilated, it grew. So your scale factor is radius over radius, or K over H, okay? So here's what I want you to think about here. Any of you watch NASCAR? I don't watch NASCAR. But they always turn what way?
Left.
Left. NASCAR. They always turn left. So if this is a car turning left in a circle, NASCAR is not a circle, but you get the idea. Which set of tires is going to wear out quicker? Their inside tires or their outside tires?
Inside.
Which one's going farther?
Outside.
The outside tires are going further, right? This distance is bigger than this distance. So their outside tires would wear out quicker, right? Okay. Our circumference of the bigger circle is bigger than the circumference of the small circle. So dealing with circumference, let's think NASCAR here.
How did you know to put K over H? So why was H?
I didn't specify on the picture, but I'm just telling you my original was the small one and my dilation grew to the big one. So it would be K over H. Say, in this setup, red is your pre-image. Oops.
Why is it the original bottom?
It's always, remember dilations, it was always the image over the pre-image.
This way.
Okay? Okay, so let's take a look at this. If I want to know how much farther we travel on one loop of the big circle, all you're really finding is circumference, right? What's the circumference of the big loop? And what's the circumference of the small loop? And we said circumference is pi times diameter, or 2 pi r, whichever one you like to think of. I usually stick with pi d, and I just turn everything into a diameter. So on the big circle, if my radius is 10, what's my diameter? 20. So my circumference for the big circle is 20 pi feet. Okay? What's the circumference of the small circle? 14 pi, pi times diameter, feet. The question is, how much farther do you travel on one loop of the bigger circle? What do you do? Subtract them. Yeah, 20 pi minus 14 pi means you go 6 pi feet farther on the outside loop than the inside loop. That NASCAR driver is putting a lot more wear and tear on those outside tires than the inside tires, right? Okay. Almost there. Wrap it up. We're gonna wrap it up. One thing I want you to note is the difference between these words, arc measure versus arc length, okay? A measure is a number of degrees. A length is like centimeters, millimeters, feet, inches, right? Those are two different things. Look at this picture. If these are concentric circles, if this is a 60-degree angle, and I ask you what's the measure of each of these arcs, the blue and the red. What's the measure of the blue arc? 60 degrees. What's the measure of the red arc? 60 degrees, okay? Their measure is the same. Is their length the same? No, the blue one is obviously shorter than the red, okay? So pay attention to the wording there. Arc measure versus arc length, different things, okay? Okay, that in mind, I'm gonna give you a formula for arc length, not arc measure. You know how to find the arc measure, it's the same. Here's your formula.
It was 60.
I told you this one was 60. I gave you the inside one. Okay, so the arc length formula is this. L equals, and this is on that formula sheet that I gave you. It's in Canvas. Okay, here it is. The length of an arc is a fraction of the circle, the measure of the arc over 360. So how many degrees over 360 times the whole circumference, right? Pi d is circumference. So the measure of the arc times the circumference. Did you get in trouble?
No.
Oh, just want to come hang out with me again? So that's your setup for this, okay? I'm going to do one quick problem for you. The bell's going to ring, but stick with me. If I want to find the length of RS, okay, the length of this arc, I'm going to do the measure of the arc. How many degrees is that arc? 90 over 360 times pi times what? 12, the diameter. Okay, now here's what you do. Ignore the pi, plug that into your calculator. 90 divided by 360 times 12 is 3. Then attach your pi, then attach your label. Okay, that's what you're gonna do, you too. The second one is just like it. I can do that with you tomorrow.